All right, as we continue our work on slope fields, this is question number 4 in your handout, your notes package. You should have in front of you. If you don't have the notes package and you want to head back over to mrmathwell.com, it's this one right here. So this is the one, and we are on, there's number 2, we did number 3 matching, and number 4, this is where we are here right now. So it's this one's a little bit easier than the one yesterday, I think, because what we're trying to do is match the slope fields now with a solution to a differential equation. So if you're given a solution to a, what's going on? If you're given a solution, try it again, solution to a differential equation, then match a slope field, okay? And then really, compared to what we did yesterday, so this is what we did yesterday, we were given a slope field, and then we were given a differential equation. Well, we had to do a little bit of work, as you see over here on the side. We had to do a little bit of work to figure out what the solution actually looks like, what the function actually is, and then match it. So this one, arguably a bit easier. It's taking out one step there, and so what we're given is we're given on the second page. You're given solutions. So this is the solution to the differential equation y equals x, and then now what you're doing is just going over and finding the slope field where y equals x would slide nicely into. So for example, this one right here, this would not be the proper slope field for y equals x because all of these slopes are contrary to the line. They do not look like they are slopes for the line. And if you go back to, looks like letter F right here would be pretty reasonable for assuming that this is the, oh wow, my tablet, okay, sorry. Is this frozen? I'm sorry. What did you say?
You just said F and you meant C.
Oh, what did I say? F? Okay. So yeah, C, letter C, this one. This was where y equals x should fit into, so this one is C. This is a solution. I'll skip down to number 3 here. So number 3 is y equals e to the power of x. So where do you see y equals e to the power of x on this paper? Any guesses? It looks like F right here. So, and again, if you want to just draw it in there to see if it actually might work, yep. That's exactly where it is. So that one's F. And y equals x cubed. Definitely wouldn't be this, well, I suppose it could be this one. This one looks pretty sine or cos-like. Do you see a y equals x cubed anywhere there? Yeah, h is looking pretty good. If you were to draw this here, sort of like, that would fit into that slope field right there. Very good. H. Okay, so again, take a few moments, and I'll try and get all this on the screen. It'll be really small for you, but try to take a few moments and compare the solutions with your slope fields there. Okay, so here's the solutions. Any questions? Anybody have any problems with those? You get those got it nailed? Okay. Good one to remember, something like y equals the square root of x. Okay, that is non-existent when x is negative, right? You can take the square root of a negative, so you have no slope field really in the negative area so that's j, obviously. And yeah, just a couple things to remember here. If you're given questions like this on the AP exam and you're given a solution, then it's this exact graph that you're looking for to slide into the slope field. But again, if you're not given that, if you're given a differential equation like we were over here, you do have to find the solution first. So you do not try and slip, well, in this case it would be, so for this one, you do not really try and slip sine x into the slope field because that's part of the differential equation. Instead, you try and slip the antiderivative of that, or negative cos x. So just as long as you got that figured out. All right, let's take a look at the next page then, page 618. And it's a great resource here, Mark Sparks, 212, a complete course here. It's an excellent resource. So credit to Mark Sparks. Okay, shown below is a slope field for which of the following differential equations. Explain your reasoning for each of the choices below. All right. Now, this is going to be difficult, very difficult for us to take the integral of these functions. So that's not really an option for us, okay? I'm going to show you another way to look at this. And again, it's just working backwards from drawing the slope field. You may have to do this. You may have to run some examples here. You may have to do a little trial and error in a sense. But we're running backwards now from drawing a slope field to identifying the differential equation from the slope field. So what I would suggest that you do is to look at the regions of the slope field that yield horizontal tangents. Because all of these here that you see me circling, these all have slopes of 0, or the dy dx is equal to 0 for all of these points. All right, and that might be the good place to start. Another good place to start, if you can identify where you have a positive 1 slope, that would be a great place to start too, or a negative 1 slope. So I would look at these sort of 3, and the zeros I think would be the best. So let's just run through. This point right here appears to be negative 1, 1, okay? So off to the side, I'll just put negative 1, comma 1. That's this point right here, and it has to be a slope of 0. The derivative has to equal 0 when I put x equals negative 1 in and y equals positive 1 in. So does that work here? Well, negative 1 times positive 1 is not 0, okay? So it doesn't appear that a is going to be the one I'm looking for. Although, that you can probably cross that one out. What about this one? Xy, so that's negative 1 minus y, which is positive 1. So negative 1 minus 1. Ooh, that's negative 2. So at negative 1, 1, I don't think we have a negative 2 slope here. So it doesn't look like it's this one either. All right. What about this one? Well, this is negative 1 plus 1. So that does give me 0. So C could be an option because it seems to work for that point. I'll run through some other options and just see what else we can eliminate. Xy plus x. So this is negative 1 plus a negative 1. Boy, that doesn't work either, does it? So it looks like we can eliminate this one, and this one. This one, E, is interesting. This one has, y has no effect. That's what this one is saying. Y does not have any effect on the value of the slope. But what you see happening is, it looks like y doesn't affect the slope here. Okay, that's true in this column. But for lots of the other columns, do you see how the slopes are changing as y changes? Because these have all the same x value. So if this was the one, then all of these slopes should be the same in the vertical column, because whatever the x is, that dictates what the slope is, nothing else. But here, clearly, if y changes, we have a slope changing. So I would say this one you could probably eliminate too. So let's check a few more just to be sure here. Another 0 would be, let's see, 1, 2, 3, 4. So how about this one? The point 4, 0. Let's see if that works. 4 times 0 is 0. Plus y is 0. That seems to work. Let's try a slope that appears to be 1, and I'm guessing this one is 1. So that is going to be 0, 1. All right. It might be difficult to know for sure if that's 1, but if you can determine that that's 1, let's try that one. So this is 0 plus 1 equals 1. Yeah. So everything we try seems to work, so it looks like your answer is C. Are you guys okay with that?
Yeah.
All right, let's take a look at the bottom half of this same page. Consider the differential equation dy over dx equals x over y. So the slopes in the slope field definitely are determined by both values of x and y. On the axis below, sketch a slope field for the equation. Okay, let's work on that first. So 0, 0. Okay, so 0 divided by 0. This would be a case where you're not going to put any kind of slope there, are you? 0 divided by 0 is meaningless, so we're not going to put anything there. What about 1, 0? Well, that's 1 divided by 0. Oh, nothing there either. 2, 0. So wherever y is 0, we have a problem, right? So we're not going to put anything on the y-axis or x-axis here. So let's move up to 1, 1. 1 divided by 1 is 1. Excellent. Look at this. 2 divided by 2 is 1 as well. Negative 1 divided by negative 1. So here I'm finding some patterns right away. Those ones all should be slope 1. And then you can move out from there wherever you determine. I'm going to do 2, 1. So 2 divided by 1 is 2. So I'm going to make this just a little steeper in line with this point down here. That's a 2. And so on. That's 2, 1. So 2, 3. So 2/3, I guess, right? 2 divided by 3. 2/3. So let's see. 2 over 3. So I'm going to try and line that up roughly with, that looks a lot like the 1. It shouldn't. There we go. So again, do the very best you can to kind of judge the slopes between each other. And yeah, so if you remember the lesson from yesterday, go ahead and complete this slope field for this question. So here's the slope field. Just a reminder, whatever your point is, x, y, just do x divided by y, and that's it. So let's see, over here, -2, +2, so it's -2 over +2, so that should be a -1 there. -2 over 3, -2/3 should be this one here, a little bit flatter. We do have a bit of a pattern emerging too, that they're kind of opposite on either side. It's symmetrical about the y-axis here. So that is something that you might notice. Symmetrical about the x-axis, really, I guess, too, in a sense. But I'll give you another minute to kind of finish that up on your own there. Okay, so B, sketch a solution curve that passes through the point 0, -1 on your slope field. Okay, so 0, -1 is right here. Okay, so what might this solution look like? This is going to be a tricky part here. Wherever you see an oblique line that has all the same slope and it kind of goes along with this line, that's probably going to be some kind of asymptote there. Okay, so that's, I think, this y = x line looks like an asymptote. And if that's the case, and we know the graph is a function, it's only going to be on one side of this sort of asymptote, and this is where it passes through. So look what's happening to the slopes here. It looks like this is going to be coming kind of like this. Whoops, it shouldn't touch that. Let me just try that again. So it looks like it's going to come like that. Right, smooth curve as you can possibly get there. There we go. And then on this side, it looks like it turns down a bit, right? So, we do notice that these slopes are all the same here too, correct? So we do have another asymptote here, which makes sense because what I've drawn here already is that this graph seems to level out here. Right. Now, could it be above here as well? I guess, is there a strong indication that this is a function? Let me see what it says here. Is it a function? We would have some functions that would be, I mean, we know of functions that are like this, right? Like that. We could have functions that are like this, but we could have some graphs that technically aren't functions, I guess, that, we could have graphs like this, right? Plus or minus. You could have circles, right? That are made up of two functions. So there could be a set of two functions. If you're just asked to sketch a solution curve that passes through, find a particular solution. This is function notation right here. See that? So in that case, you shouldn't have a graph that fails the vertical line test, I guess. So I guess that's what I would see here. This says f of x. That means function notation. So you shouldn't probably have a graph that goes up like this as well. So that probably wouldn't be good. Now, let me just check something. All right, so for letter C, if you don't know or haven't learned about differential separable differential equations, then you're going to want to watch the video on separable differential equations. But there's a little bit of a twist on how to find this actual particular solution, doing it mathematically. So we've sketched what the particular solution looks like here, but to find it mathematically, it looks like this. So the equation that we are given, the differential equation, is dy over dx equals x over y. Now, when we have x and y on the same side here, it's really difficult to take the integral of both sides, because what do you take it with respect to? Well, this one's with respect to x, but what about this one? With respect to what? Well, there's two variables. So in what we need to do is we need to separate this equation, and so that we have only x terms on one side and only y terms on the other, and then we can take a look at the integral. So what I'm going to do is I'm actually going to, in a sense, multiply both sides by dx and multiply both sides by y, which is going to give me a separation of the variables. So I have y dy on this side, and I have x dx on this side. And this is a very simple one, but it's easy to separate the variables this way. And now that we have only y terms on both sides, I can now go ahead and integrate both sides with respect to y on the left and with respect to x on the right. And that will give me 1/2 y squared on the left side, and this will give me 1/2 x squared on the right side. And yes, we do need to add the plus c, and as I've mentioned in the lesson before on this, we do not need to add plus c to both sides, just to one, because whatever the constant is, two constants can be combined into a third constant. So we don't need two constants, we only need one for this one single equation that we're going to end up with. So we combine the two c's in a sense. So here's where we put in our initial conditions, which we see is x equals 0, y equals -1. So we'll do that, and it should look like this. 1/2 -1 squared equals 1/2 0 squared plus c, which will give us positive 1/2 equals c. So that's our c value, and now I can go back and put this c value into this equation right here, the second step, and that's going to look like 1/2 y squared equals 1/2 x squared plus 1/2. And of course, when we separate variables, we do have a little bit of work to do after we put the c back in, because we may or may not have y equals, right, all by itself. So in this case, we don't. We have to multiply everything by 2 to get y squared equals x squared plus 1. And then to solve for y, to actually determine what the f of x is, we need to take the square root. When we take the square root, we do have to remember that we have plus or minus. And that's where, as I just mentioned, remember, you would have two separate functions here. Okay, these are two separate functions that are y. So one would be this one up here, and one would be the one down below. And so in this case, you don't want to list two, you only want one particular solution. And so we have to determine, given our initial conditions, which one is the correct particular solution. And because our initial condition said this was one of our points, then I take the negative version and not the positive version. So the version that would be down here. So that would be y equals negative root x squared plus 1. So this is my answer. And to check that, I can certainly check that with my initial condition. So -1 equals -0 squared plus 1. And that's going to be -1 equals negative root 1. -1 equals -1. We're good to go. So that is my check. This is my particular solution. So that's how you do C. And that's your solutions for that page. Anybody have any questions? All right, so please work on day 60 homework, 1, 2, 3, 4 here, 1, 2, 3, 4. And then in your package, you have a number of AP calculus questions, which I'll want you to attempt and work through. And yeah, these are some answers I'm showing you, I guess. But work through those questions as well, and we will get through this one, and so there's 4 or 5, I think, that I've given you in this package to work through, just lots of practice on AP style questions. So that's the second lesson on slope fields, and you can pretty much, finish that package up to, and we will do some more work on separable differential equations on the last half of this notes package.
For marking leave,